Hi everyone, welcome to another Haskell Study group. I'm your host Ron Vadum with Atlanta Functional Programming. Today we're going to be discussing a topic that we've actually been covering in bits and pieces, but in a very informal way, type classes, in the last couple of weeks. Type classes is a very important concept, and you often in early on in your Haskell journey encounter it without really understanding what it is. But it's one of the more fundamental pieces of the Haskell type system that allows you to essentially implement fairly generic algorithms and operators. It also, in a sense, is a piece that enables you to add constraints on top of those generic algorithms, which I've addressed and briefly mentioned last week when we were talking about types. Today we're going to be discussing what exactly a type class is. What exactly a type class is. We're going to cover some basic type classes that you should be aware of, such as EQ or D for ordering, show for converting to, like, say, a string or displaying this into the screen, and others. But we're also going to be covering how to create and write your own type class instances. Okay, this is a very important piece that will enable you to essentially leverage some of the available type classes that are inside the Haskell system. To begin with, I wanted to mention just a couple of announcements. There was a couple of comments that were brought to my attention related to material and how to kind of leverage some of the series and discussions that we've been having on the Haskell Study group, and supplementary material, and have a way to actually keep track of and be able to read ahead so that folks can actually kind of come somewhat prepared with questions or thereabouts during our discussions in these topics. As I mentioned before, but I'll briefly mention on this stream, we're using a book as a basics material for the topic listings. Obviously, we're trying to cover some of these topics in a little bit more detail using other various materials ourselves, but the topic listing and to follow along really is based off of the book. It's called again. It's called Haskell Programming from First Principles. It's a book that you can find available and purchase on Amazon, as well as on LeanPub. I think there's a couple of other places where you can purchase it by. It's by Christopher Allen and Julie Marnucci. It's a very good book with a good coverage of exercises and things like this. But obviously, some of the material, as I've been encountering, at least as I've been reading through the material, I felt a couple of other books did a better job in providing some additional context into some of the concepts. So we've been using this book kind of as the topic listing for giving folks at least some material to follow along. And in addition to that, I'm using some other books to just fill in some of the gaps where I felt they did a better job describing some of those things. Just so that you guys are aware. Today, specifically in terms of that book, we are covering chapter 6 essentially. In that book has a basis. Some of the material that I'm getting is also from other books like Learn You Haskell for the Great Good, which I thought did a pretty good job on explaining some concepts on type classes that I'm mixing in with some of the stuff that's here. And then we're going to use some of that information there. I'll post, as a result of this, both to the meetup for folks who are on the meetup page, as well as the YouTube description here, the supplementary, the material that we've been kind of using to kind of cover these concepts as we're going through Haskell. So let's get started. First, I want to state at the outset, because this is kind of, I know it will sound obvious for folks who are who have been following along, or even who has some level of Haskell experience, that type classes are very different than types. Okay, a type is I think it's important to know what the difference is to understand what a type class actually is. Okay, they are type classes can be thought of as a generalization over one or more types. Okay, this is one point that I want to kind of really stress. Okay, can be considered a generalization over a set of one or more types. Okay, you could think of a type in a very loose way as a set of objects that have certain characteristics with each other. Okay, this is how primitive types are defined. If you think about, for example, fixed nums or fixed precision integers. Okay, all the members of the fixed precision fixed nums are numbers that can be represented within a particular number of bits. Okay, oftentimes it's going to be the size of a word inside of a computer architecture. Okay, so in 64-bit architectures, you're looking at 64 bits. In 32-bit architectures, a fixed num would be 32 bits, and so forth. Okay, some languages, such as Common Lisp, where they're based on a tagged-based architecture, where the actual word size encodes some type information, the sizes get adjusted based on the number of bits required to actually keep that type information. Oftentimes, it's going to be like 2 bits for the type information, so you're looking at like 30 bits for a fixed number and so forth. But the point is each number in each that's a member of this set. Okay, if you can think about it as a set, they actually adhere to these characteristics, and as long as they adhere to these characteristics, you can then do certain things like, run certain operations like additioning, arithmetic operations, maybe even constructing new versions of these, as long as they are within the context of that fixed representation. Where a type class falls into this realm is, it's not necessarily, and this is the second thing, it's not necessarily a type description, but it's a set of behaviors. You can think of this, okay, a set of behaviors that, or a set of operations, if that would be more general for you, okay, because set of behaviors kind of indicates or implies a more object-oriented kind of style if you use behaviors for function and methods and so forth. Okay, they consist of a set of operations that these one or more types that implement the type class would have to adhere to in their consistent manner in order for the operation to actually execute. Okay, we'll see an example of this when we are when we're talking about the EQ type class, and how it's implemented and when we're exploring it in a bit. For folks coming in from other languages, other programming languages, especially object-oriented programming languages, it might help to at least start out thinking that type classes are similar in fashion to interfaces, data interfaces. Okay. The reason why I'm saying that they're similar and can work across multiple data types is because depending upon how you're defining your data interface, you might be creating necessarily a type family versus something that is a more often than not a cross-cutting concern. Like an example of this would be in the case of what we saw with the show type class or the EQ type class. In other languages, you might end up implementing like a displayable interface where you need to add one or more operations across one or more types in order for it to be displayed inside the print screen, and that's a cross-cutting concern regardless of what type you have. As long as it implements that display method, it'll go and do its job, versus something that is more that's taking more information regarding the set of types that you're dealing with and their characteristics, and just uplifting their operations so they have a common, consistent API. An example of that is kind of the reflective API that's often used when you're talking about single object hierarchies. That is one way of creating sort of a type family versus something that is kind of a separation of the operations from the actual implementation altogether. Okay. So this is the other point on this. With type classes, you do have essentially in Haskell implement a form of ad hoc polymorphism. Okay, so what we're talking about ad hoc polymorphism, if you recall our discussion last week on the different polymorphic polymorphisms that are available inside Haskell. The authors of the Haskell programming book call the ad hoc polymorphism that uses type classes actually like a constrained polymorphism, where you're adding type constraints essentially in terms of the operations that need to be present in order for an algorithm to execute. But I feel ad hoc is more correct, although the constraint polymorphism idea is a little bit more descriptive. The technical term that's often used to actually talk about these polymorphic functions is ad hoc, and what that means is you can add additional types to this list of implementations of type classes, and we'll talk about what an implementation is in terms of type classes in a minute. But once you do that, you've essentially extended the type system so that it can operate on a particular set of types with respect to a specific set of operations. Okay, this is why ad hoc polymorphism is often used in a lot of languages like C++, or statically typed languages like C++, Pascal, or even Oberon, Go, and so forth, because you can implement ad hoc polymorphism by simply essentially writing a new function with the new different types. Okay, where type classes in Haskell and those differ is that ad hoc polymorphism in the other languages, because you are documenting strict concrete types in your function type signature, if you need to go and implement, say, a generic algorithm there, you won't necessarily be able to do so because those types don't necessarily inherit. They don't necessarily fit some sort of type hierarchy. If you end up using objects, you might end up implementing that ad hoc polymorphism as a mixture of ad hoc polymorphism using interfaces versus concrete types. But you're now kind of using two different types of polymorphism to get the same effect, okay, to write a generic algorithm. Now, in languages like, say, C++, there's another form that's that's in there using, say, templates, but even there you have this issue where template instantiation, if you end up accidentally saying, if you have a function template and you didn't use any specializations, for folks who aren't familiar with C++, there's a way of doing template specializations where you can instantiate a template at compile time. If you're not doing that, but if it encounters a new function template that may be misused in the way that you were intending to use that function template, and this is before C++ 20 and the advent of concepts, what would end up happening is you can instantiate a new version of that template, and now you have a function with a different type signature, which makes everything compile, but it may not necessarily give you the expected result because the function template that was used was the wrong one that you want to use. Okay, and now with the advent of concepts, which is very similar to type classes in many respects, it kind of fixes that kind of issue. So you end up getting some of the same stuff that Haskell has in terms of that functionality inside that language. So the formal way that, as I mentioned, is about type classes. They are a generalization for one or more types that consists of a set of operations. One way of thinking, another way of thinking of this is type classes essentially define and execute a standard API or a set of features on those types, and this is defined by, say, the Haskell book. I thought I'd mention this definition too as well. I had another way of thinking about what this is. What a type class is ultimately defining. But all these 5 characteristics, okay, of type classes, okay, are nothing more than I just realized that I keep on, these are 2 separate words, not one word. All these characteristics can clearly show you that they are very different than what a type actually is inside of Haskell, all right? Or even when you're talking about interfaces, how the difference is between an interface and one or more types, okay? A type class is nothing more than a set of features or a set of constraints that a type that implements that type class has to define in order for it to actually derive that particular type class and ultimately use those algorithms and those operators that are defined by that type class. Okay, I hope that this particular thing makes sense. We're going to see an example in just a minute, but conceptually, you thinking of it like an interface with a defined API will get you pretty far ahead in terms of understanding what a type class is with respect to abstraction inside the Haskell type system. Types implement type classes, and more specifically, using Haskell terminology, they tend to derive those type classes, okay? One way is to do a manual derivation where you essentially, quote-unquote, instantiate the type class on that particular type, where you're defining those set of operators for that particular type class for that type. or you can do some automatic derivation. We'll touch base on that in just a minute. So I think the easiest thing to do to begin our journey on this, and let me just save this, is to start with what type classes are available for a primitive type like bool. Okay, we've seen this type definition before. Recall that the type constructor is consistent of the type constructor on the left-hand side and the data constructors on the right-hand side. Each one of these is a data constructor. When you are defining instances of your type classes, though, okay, you are actually working on the type constructor, not necessarily the data constructor. I've never seen examples of type classes being implemented on a specific data constructed type. All right. I'm just mentioning that just so folks who might be wondering if you can do a very specific constraint on a type class for a very specific instance of a data constructor, I have no idea. I've not seen any examples of this. Often it is implemented this way. You have the instance, you have the type class name, and then you have the type name. Okay. If we look at EQ from a top level, okay, I think it's important to explore the type classes themselves. You're going to see the operations defined on EQ, but to get started on what this is telling you in terms of bool, each one of these instances are defining a set of constraint methods that are implementing this type class for this type. And we'll see in a minute what those definitions are, although I don't believe the Haskell REPL will, or if there's a way for the Haskell REPL to actually spit out the implementation for a particular class instance, I have no idea what that specific way is yet. There are many options inside the Haskell REPL that gives you some way of looking through the source code, but oftentimes I think you have to actually have the GHC source code to actually go and see how specific implementations are done. Okay. Each one of these type classes represents a different set of behaviors, a different set of features. Okay. Obviously, this should be something that you can just understand by the names being different. EQ, for example, deals with equality. Order is talking about ordering things in some sort of sequential order. When you're talking about enumerations, these are dealing with specific things that can be enumerated, and the enumerated type class we'll explore each one of these in just a minute. Bounded is more about creating sets, specifically things that have an upper bound and a lower bound to check set membership. And show is what we talked about earlier. It's for rendering things often converting them into strings. So show actually implements kind of like a two-string method that we'll look at in a minute. Each one of these ends up creating for Boolean a separate type hierarchy. Well, each type class represents a separate type hierarchy. If you want to think about it this way, it'll make makes things simpler for you. Then go for it. But the specific things that you need to just be able to be to know is by having these operations defined on a specific type, these type classes can then be leveraged to create algorithms for a set of types that adhere to that type class. Okay, so this is one way you can get your polymorphic, your ad hoc polymorphism that we were talking about earlier. So let's dig into one of these type classes. Okay, I think the easiest one is EQ for the matter. EQ, as you can see, is defined for a lot of different things. Okay, and if we look at the actual definition, this will tell us what the template is for a type class. Notice a type class is defined as a class. Now, coming in from other languages, I know that this is going to be somewhat jarring. All right, but this is how you define a type class. You start with the word class. You name the name of the type class, and you have to specify a type variable. Remember what we talked about type variables last week, which is lowercase letters are often used to represent type variables inside Haskell, and these are generic types. We don't know any other type information that this is EQ of some type. Okay, you can think of this as the any type, right? But really it's any type. Okay, not necessarily a type called any. All right. The next two things that you should see here is very, very important. So we have this type class definition, and then we have the where clause. And remember, where allows us to define certain constraints. We've seen where in other places. This syntactically is very similar to what we saw its use in some sort of scoped cases. The only difference is when you see a where keyword inside a class definition, like here in the type class, you're not necessarily defining concrete methods. What you're actually defining is a set of method signatures in this particular context. Okay, so this is just some syntax understanding. When you're defining your type class, where must be present inside this line in order for you to define the additional operations associated with the type class. Okay. So then we have our next two things, which are our method signatures. Remember, I recall that each of these are technically infix operators, okay, but they're defined actually like at any other function inside Haskell, which is first off, the name of the function is defined first. Here, if you remember again, the operators, for operators to be defined, you must encapsulate them with parentheses. So you wrap them around parentheses. So this represents the equals operator, and then you're saying that it's defined as, and you have our standard function signature, which we talked about before. Notice when you're looking at these two things, something should become very, very apparent. Okay, they're all the same type variable. Okay. I know this is this is an obvious detail, and you may be wondering why I'm bringing this up, but it becomes important when we start talking about how to leverage some of these operators inside our code. Okay, what happens when you actually go and use this with the specific values? All right. And here, what you're seeing on top of this, whenever you do info on any type class, you're seeing a list of all the specializations associated with this type class, okay? And as you can clearly tell, EQ is defined on a lot of different sets of types, many of which are different types of tuples, essentially. That are being used in various different things. All right, and it's also used oftentimes in it's already defined for integers too as well. Are there questions on this? Okay, so let's talk about usage of this. So you've already used a lot of these operators, which are defining different types In particular with EQ, we've actually used a lot of the EQ equality types when we're doing equals and not equals. The one thing to note is what is the type that's ultimately going to be defined when we do something like, say, 132, and what's actually happening behind the scenes with the equality operator. You could still do specializations associated with these type classes, but ultimately your signature that you're getting is going to have one specialization, but it also keeps track of the fact that originally the second argument was associated with the first type class, which is EQ. The main thing that I wanted to bring up and why I brought up the method signatures, okay, keep this in mind here, is that when you are, since Haskell is essentially an implementation of the lambda calculus, okay, when it's defining some things, and specifically the type lambda calculus, it will adhere and first construct the types that it needs before it actually goes and does beta reduction, and then essentially applies the function to the arguments. Okay, why that's important is because when you start doing things like saying mixing types, okay, if it's not defined here, you're going to end up with errors like this, which is cannot create instance of num character arising from the literal 32. All right. What this is essentially trying to do is it's trying to cast your string that you just passed in into a number, because since we specialized, the first argument was inferred as being an integer. The type signature of let me see if I can actually keep that there. The type signature of the type signature of the actual function that we're actually defining, it has been converted into something along the lines of this. It's not necessarily going to be this, because you see that this is a numeric type with the type variable, and it's trying to verify it's going to be a numeric. So you could certainly do something like 132 minus equals 132.1, and it could still allow you to do comparisons. But because those are both numeric types. But the actual type signature that was defined essentially was something along the lines of this, based on what we saw earlier. So in this case here, let me just close this window so I can get the example up again. If we did this again, you get this instance here, and what this is showing you is the type signature of this guy, which actually we have open up here, gets converted into essentially something along the lines of this. EQ of some numeric type, okay, num of some numeric type, okay. So what it's doing is it's taking the first argument that you see here in this signature, specialized it on this tuple, okay, and saying that not only does this have to be implementing the equality operator, because remember what this is. This tuple here is actually saying this is the set of type classes that the type variable has to implement in order for it to be a valid type to be passed in and bound to the type variable. Okay, so the first thing by it encountering a 132, all right, which is a numeric type, we've implicitly added an additional type constraint into the lambda signature, all right, into the function signature. This is how all the type inferencing stuff works that we talked about last week. Recall in the type inferencing, it is taking the first argument and it's actually going through and inferring the types, and then what it does is it'll take the type class associated with it and does a lookup to check to see if there's a function defined already for this type class or for this specific type that's available. Okay, it'll start with type first and then type class and goes up because it'll try to execute the very specific functions first. Okay. By it seeing this 132, we added this numeric type signature, right? So now let's go back to what we were trying to evaluate. Okay. So remember, this is the same as, and it'll be easier to actually see this by doing equals equals 132 hello. All right. You'll see that this ultimately is recognizing that, okay, 132 is a numeric type. This has now become essentially this function signature. Okay. Hello is an equality type, and we could see that hello is an equality type here because we can compare strings. Okay. So the next thing that it's actually doing is okay, so we've satisfied the equality type class. Can we actually satisfy this type class? And what is it going to do? It's going to attempt to check to see if there's an instance of numeric on type of string. All right, and that is what this error message is telling you. Okay, it is looking up in the list of available instances, okay, defined for that type, which is a list of string, to see if we've defined that type class for that particular type. All right, specifically, did we define the numeric type class on the list of string? All right, and if we didn't, it throws up that error. Okay, that's how you can read this error message inside of the REPL. We've encountered a number. We've said that this number is now a constraint on top of this. Can we convert this number into something that can be used for this comparison? That's how it should all work. Now, you might be wondering now, does this work true for equality 132? It's going to give you the same error message. And again, the reason why is because although the operator is commutative, right? Equality is technically A equals B, A, and A equals B just has B equals A. So if you change the arguments, equality is technically commutative. In terms of the type inferencer, it's going to deal with precedence on top of the type class that is more specific. So in this case, list of characters is a type alias that is associated with equality, but 132 is a numeric type, and although numeric does implement equality as well, the numeric type class is more specific, so it gets higher precedence in terms of what should actually be looked up. All right, and that's what's ultimately being used for this comparison. Okay. This shouldn't be really a surprise because, as we saw with the actual type class signature, recall that the type class signature already gave us this information. All right. It says that these both have to be the same type. And the same type doesn't mean the same underlying concrete type. That means that that type variable, whatever type class constraints were defined on the type variable, all instances available in the signature must adhere to those type class constraints before they get bound to the appropriate argument, and ultimately the function will get evaluated. Okay? Does that make sense for folks? I know I'm spending quite a bit of time on the type signatures, but understanding how these type signatures work, understanding how the type constraints work, and understanding how the type classes ultimately get employed by the inferencer to actually guarantee that those type variables are bound to arguments that are valid. All that's important in order for function evaluation to do its job, which is actually executing, evaluating the function using some form of beta reduction. Okay, these are all the same moving pieces, a part of the same infrastructure that actually ends up working together in order to guarantee that when you compile your code, all right, you're guaranteed that if the signatures were inferred correctly, that the code will just work. Okay. Now, again, I say that very with the caveat that you've actually implemented your requirements accordingly. So this does not actually um, eliminate testing or eliminate unit testing or specification testing or property-based testing or any sort of testing that you might want to incorporate in order to verify your programs. But it does certainly eliminate a certain class of errors that you have to do additional testing for if you were using a dynamic programming language such as Python or Ruby and so forth that doesn't provide the kind of type information and type guarantees that are necessary in order for you to actually verify just the requirements and not necessarily the arguments being passed in to the functions to make sure that they are actually valid arguments coming in. Okay, you have to do a lot more defensive programming in those places to ensure correctness, where the type descriptions and the type class descriptions will give you some sort of safety in terms of at least saying, well, we might be still getting necessarily bad output because we may have implemented the algorithm wrong, but we can at least guarantee that when we compile the code, the type characteristics and the type arguments that we're expecting as inputs are actually coming into the function signature because the type system has encountered that and enforced that for us. So let's look at another example. Let's look at another equality example. Does yeah, so let's look at how this might work with, say, tuples versus comparisons. So we're going to do a couple of more equality examples just to illustrate the different types of errors that you might get. We've already encountered and talked about integers, and we saw how the numeric type class is more specific, and specificity is going to indicate which one is going to actually take precedence and actually being looked at first. Okay, remember that. So if we do the same thing with, say, let's try AFP or something like that. Notice that in this case, what it's giving us is different than what we got with, say, string, and that is because of the fact that the two types that we're getting, one is a generic type of two type variables, A and B. That type doesn't necessarily match with the actual type. The reason why we're getting this error message versus what we saw before with numerics is for a very specific reason, and that is integers or any numeric type and all strings which are type alias holistic characters, they all have a common ancestor, all right, in terms of a type class that is implemented by both those types, okay? In this case, they look disjoint. So what they're doing is just first checking to see if the types actually uh, uh, fit together in some way, shape, or form. And clearly there isn't one here, which is weird because I thought we saw equality for these tuples. So it might be based on some other type class where a list of characters and characters are getting enforced in a different way. So let's see what happens with this signature here. Let's see. Info equals type 1, 2. Error parse incher. Really? Okay. Let me see if I can do type then. There we go. So by specializing interesting. Let's see what this is doing when we do it says that it's still okay. So let's see if we change this, what happens if I do this. We get okay. So this is explaining what I was trying to show earlier. Okay. So let's see why this particular example that we saw earlier was giving us this error. Okay. Now notice if we switch the arguments, you're going to end up getting, and this is what I was trying to show you earlier, different signatures. Okay. In one case, we saw couldn't match expected type tuple to match with actual type list of characters. Okay, which is the string. All right. In the second example, we saw in this particular example, we saw couldn't match expected type string, which again is a type alias for list of characters, with actual type tuple, okay, of two type variables. Although the operator, like I said, was commutative, again, right, there are certain rules in function application that Haskell implements, and this exactly is the realization of the type lambda calculus. Remember, in beta reduction, okay, when you're binding variables, okay, you are binding the leftmost variable first, and then you are reducing and lopping off the outermost lambda argument in order for you to complete the partial evaluation and return essentially the lambda instance with the bounded argument and the remaining free variables that are available for further reduction. Okay. In this example, the way the type system works, okay, and the type lambda calculus, especially as implemented by Haskell, is the leftmost argument determines what is the type signature is going to be. Okay. In this case, it's going to be essentially the string is, remember, on the left-hand side of the infix operator, so that's actually what's determining the actual type signature. Reason for this is the way this is essentially treated, and I'm just making this into a comment so I can actually write this. This is actually the same as hello has the first argument, 1's comma 2. Recall that we could run this in a prefix style, and the left-hand side of the infix operator becomes the first argument. The right-hand side of the infix operator becomes the second argument when we're writing in the prefix style. So when you're looking at it in this function call form, it becomes obvious what is actually the type signature, right? The leftmost argument, which is a string, will end up enforcing that the type variable, because remember here in our type signature, A is a generic type variable that needs to be consistent across the type signature. So the first argument is going to be a list of string, which means the second argument must be a list of string. Now, when we look at the second argument here in this function signature, we see that it is a tuple. So obviously, the generic types, the two types don't match with each other, and we end up getting this particular error, right? The one thing to learn from this is your type signatures, okay, if they match some sort of equality, will end up giving you a very different error message to see if they can convert things. In the case of our numeric type versus string example, versus in this case a straight nominal type comparison. We figured out that the first type is list of characters. We figured out the second type is some sort of tuple of two variables. They don't match, so we can't actually convert them, and there's no way of necessarily being able to convert one over the other. All right. Let us check out one more thing, which is this one is okay. So far we were talking about pairs, and we noticed that instances of pairs have some sort of equality operator already defined by them. Well, if you actually look at the tuple operator itself, you can see clearly that there is a list of instances already specialized on it, one of which is the EQA and EQB operator. The EQA, EQB instance that is which is implemented has equality of this pair. All right. This implementation is one of the reasons why we're able to actually do comparisons between tuples of pairs. In fact, we could technically go, I think, as far as triples or even further than that. I think it's up to quintuples. I think they defined the pair operator, the tuple operator specializations for equality all the way up to pairs of 5. Although, because there's a rule of thumb again, if you're using number of tuples greater than 5 members, what you really should be implementing is some sort of composite data type and not necessarily the data type of a tuple, just because that makes things much more unwieldy for various reasons. Okay. So one thing to note is this here. Okay. This is a very different signature than what we've seen so far. Okay. And in fact, as you see for a lot of these definitions, this all been defined, but it's been defined in a very specific way. Remember, this left-hand side arrow right-hand side sort of notation is associated with an additional type check that must occur in order for this specific rule to actually get executed or instantiated. All right, what this is telling you is in order for us to use this equality instance, okay, this EQ type class instance on this tuple, each one of the arguments, each one of the type variables themselves must be EQ, all right? So each one of these type variables must implement the EQ type class in order for this EQ instance to be valid and ultimately the operator to be executed, all right? We've seen this in function signatures in multiple places. But this is probably the first time I'm introducing, and you may have encountered this sort of notation when defining a particular instance itself, all right? But this is telling you one thing. You can add additional constraints on your instance to verify the input types themselves have implemented other sub constraints before the actual template, the actual type class instance becomes valid and ultimately executes whatever the specific implementation for those operators as they were defined for this type are evaluated. All right. I'm going to stop for just 1 minute and see if there are any questions from our audience in the stream. Okay. Let us talk about derivation for just a brief minute. I'm just going to briefly mention it here just because I'm sure there are some Haskellers watching this and say, well, EQ and ORD and the stuff that you mentioned, all those can be automatically derived magically, and we can implement them using the derived keywords, right? And that is certainly true. I don't remember the specific example to illustrate this. One that I think I could probably do is let me see if we can actually incorporate. Let's see if I can do this here. Let me see if I can do. These are all defined, but it is not giving me the definition of. Okay. Can't seem to recall. Let me see if there is a derives that I can actually let's see if we could use pair. So although this is mentioned in the book and other sources, this is going to go into more detail later on. But one thing to note about type classes is the fact that you could technically get them auto-generated for some of them by using the deriving keyword. I'm only going to briefly show you an example of this. I won't go into too much detail into it, but I think it's important to realize that type classes don't necessarily all need to be implemented from scratch. We will go in a minute into implementing our own type class instance, but it is important to note that some of them can be automatically generated for you by using the deriving keyword. And the way you do that is you define, say, an example like, say, creating your own pair of two integers. Okay. A, and you can add on top of that deriving and specify the type classes that you want to generate, and this automatically will generate the information for EQ and show, and we could see that if we do EQ now. I think you should see a pair written somewhere here. Yeah, this is our new instance that we've defined in our definition, and we'll also see an example of this in showing and converting things into strings and things like this. But the reason I'm bringing it up is, and you won't necessarily need to use this more specifically right now, but I do encourage you to go look into it. If there's a way for Haskell to derive your type classes for you for implementation's sake to extend the system, I think it's a good way of actually going, instead of you writing your type class instances yourself, because you're saving a lot of work. All right. But we'll be later on we'll be addressing this more and more when we start talking about data types such as pair that we saw here. All right. But this is one way of actually creating and implementing your type class instances. All right, so manually implementing, well, let me just say, writing our own type class instances. Okay. So up until now, when we were talking about type classes, we were really talking about their use. Okay, we're talking about how the inferencer ultimately grabs that information, checks to make sure that it's associated with the type class, and then executes the appropriate operator has defined for that specialization. Okay, but we have not actually yet talked about how the type system actually registers these type classes. Okay, like what exactly does that mean to have an instance of a type class associated with the type? I briefly mentioned earlier that part of it is related to the fact that an instance of a type class represents a specialization of the operators as defined by the type class on the concrete type that you've bound to the type variable. All right. But we have not actually talked too much about implementing our own type class instances, and right now we're going to start talking about it. Okay. Sometimes you will end up having to write your own type class instances, so it's important to understand what that involves. While it is certainly easy to do something like this, okay, not all type classes will give you the luxury of actually doing this quick derivation, okay, because there might be some complex rules that for a specific type specialization that you need to implement yourself, okay, and there's various reasons for this, you know, sometimes performance reasons, sometimes you found an algorithm that is works in more specific cases for your application, and the types that you're dealing with, or specialization of the types that you've defined versus other types that are available for you, and so forth. So it's important to understand how to take one of the type classes and implement our own instance of that type class, okay? Although I showed you how to generate EQ type implementations, it might most often be the case that you could just simply use the deriving of EQ. Because EQ contains only two methods, all right, equals, equals, and not equals, it's easy for us to just implement our own type class instance for EQ. Now, EQ is defined, and for folks who haven't started using this, there's a nice search engine available called, I think it's called Google, that'll allow you to go in and look at a lot of stuff that's already been defined in Prelude and Haskell and so forth. And you can use this to actually go and look at the implementation of EQ and what is required in order for you to implement EQ. We already know that in the definition of EQ is that the minimal complete definition of an instance is implementing equals, equals, or not equals. All right, that means in order for you to define a valid EQ instance, either implementing just equality or just inequality will be more than enough for you to have a valid EQ instance. You might be wondering, well, why is both of them then in the signature if we only need one or the other to have a valid instance? Well, that's because, as many of you probably have guessed, one can be implemented in another by simply doing a not. All right, so you don't necessarily need to implement both in order for it to be valid. If you just implemented one, the second one will automatically be generated based on how you implemented the first one. Okay, so let's start out with first defining a data type upon which we want to define equality on. Okay, I'm going to reference the example that I think it's an excellent example from the Haskell book, chapter 6 in the notes, that I think is nice. Let's say that we have some sort of example that we call trivial. All right. This guy is a very nice type because of the fact that this is just a dummy type, all right, that doesn't really take anything, right? And remember, this side's our type constructor, and this is our data constructor, and our data constructor can be the same as our type constructor in terms of the names. The names could be the same, right? You can create once this is loaded, you can attempt to actually create instances of this type, okay, by just doing trivial, okay, and you can see that it's getting automatically generated. But if you try to compare two trivial instances, you're going to get an error. What is this error? Well, this error is saying that we don't have an instance of EQ defined for the trivial type. Okay, so it did our standard lookup. It attempted to find the trivial type. It attempted to It attempted to look up to see if any instances were defined on it, couldn't find it, and therefore just straight up said, okay, you know what? Here's the expression. I can't find this instance. Either you haven't defined it, or in some cases, and I'm mentioning this to folks who are especially writing Haskell in files specifically. All right, your specific module may not have implemented that operator, and it might be defined elsewhere, which also causes a specific error because it means that your REPL doesn't have any idea of where the definition is. All right, so we need to go in and actually define this. All right, so one way of doing this is defining our instance of EQ to actually define to understand the rules on how this is going to be implemented, okay? And this is going to be a very trivial example because we have a trivial type that doesn't take anything, all right? To make things a little easier from the standpoint of to visually separate our data instance from our type constructor, I'm going to just simply rename this guy, although you don't necessarily need to do it. As I understand it, you can actually use both. I'm going to show you how to implement this first. Got this loaded. And what we'll do now is we'll define our instance. Now recall, to define a type class instance, you have two things here. One is the name of the type class that you're specializing on, and two, we have a type variable that we're associating with, and we're now binding that type variable with our trivial type. Okay, we're not binding it to the data constructor, we're binding it to the type constructor. Okay, now the where is where we're going to be implementing our rules, and in this case, you just need to write the constraints of the rules. All right. So here we are taking essentially an infix operation, and we are defining what is the so I'm going to write this first the way I would normally write this using the prefix operation, but I'm going to mention that we can also, and I'll show you in a minute, that we can also show this in an infix style. So we define the operator, we define the two types that we are specializing on. Again, remember, if we don't restrict the types, okay, I'm just going to mention this before I move forward here. Recall with equality that you are restricting the two arguments to a specific type rule. All right, both of them have to be the same. So that's what we're doing here. We're saying that A, the first argument A in the type signature, is of type trivial star, and the second one is going to be of type trivial prime too as well. And now we're just going to say if we get two instances of these two, we could say true. And this rule there is an error here, but it says okay for some reason. Oh, it went away. All right. Okay. So now that we've defined this rule, we're done. All right. We have now added EQ for trivial types. Okay. We've added a rule saying that, okay, if you encounter two instances of these two data values, okay, which is of this type trivial, execute this rule for this function, saying, okay, we're defining any comparison of any two trivial types as to being true always. All right, that's how you should read this. Okay. Now that we have this, we will see again if we do info EQ, our new instance in our lookup. This is something that you should get used to, especially if you're doing file-based Haskell development. Okay, when you're implementing your own type classes, you want to make sure that the type system has registered those rules and those instances before you start trying any additional things inside of the REPL. And the easiest way to doing this is, if there's a specific type class that you're implementing, just do a :info on that type class and verify that, one, the rule is there, okay, and two, it's coming from the file that you're expecting it to come from. All right, this information will save you time when you are developing your Haskell programs. Okay, it will at least ensure that it's been registered correctly. Okay. Now that we have it, we could just simply do trivial star equals trivial star, trivial prime. All right. I wanted to show this one other thing here, which is if you want to do this, you could certainly do this and this. And this also works. Okay. You don't necessarily have to name the data constructor and type constructor differently, like I said before. I think it's up to you entirely as to whether or not you feel one versus the other. I think it's good practice. I think it's Haskell best practice, actually, to have the type constructor to be the same as the data constructor name, just because it kind of matches with the rules. The only time that doesn't obviously happen is if your type is like a sum type, where you have one or more types associated with the specific type itself. One or more data constructors associated with the specific type. Like I mentioned before, this operator here, that although I'm defining this as a prefix notation, you can also write rules. And this looks a little jarring to me, just because coming from other languages, it's kind of weird. But I'll mention it here for folks who may feel that this style might be better. You could also define this instance as being trivial equals true. All right. And what this is doing is it's taking the actual infix operation, that rule, okay, and it's explicitly just substituting that with true. So whenever it encounters this rule, you are it's going to just replace it with the word true. It's going to take that rule. It's the same as doing the prefix invocation and replacement, but this infix notation, if you feel that this notation and this is more readable for you to define it, you could certainly do so. Behind the scenes, it's going to be the same rules. It's going to get converted in some form to something like this, but it will still work regardless. So if you do trivial equals trivial, this would work. If you also convert this to trivial, you'll also get the same execution, because it's the same infix operation. It recognizes that you've just you're using the same infix rule in the same way. So this was pretty easy. Let's try and do something a little bit more interesting. All right. One is we could certainly do colors. We could compare colors, and we'll say we'll define primary colors as being a type. Okay, data primary colors. Remember primary colors from your art class in elementary school being red, green, or red, green. Sorry, red, blue, and yellow. Right? Because blue plus yellow equals green. So you might want to implement this guy and write an equality associated with this. Okay. So how would we want to implement this, right? We could certainly do this by saying instance EQ primary colors where, and we need to write all the different rules associated with this. Okay. One is red equals true. We know that this is going to be true. Red is always going to equal red. Blue is always going to be equal to blue. Yellow is always going to be equal to yellow. And you know what? Let me change this from primary colors to rainbow colors so we have a little more variety. Okay, Roy G. Biv here. I'm gonna go in here. Red, orange, yellow, green, blue, indigo, and violet. Okay. And obviously, let me just put this rainbow color. Now we have our rules. All right. We're getting some weird notion here. Incomplete. Oh, right. We haven't implemented all the patterns yet. Okay. So now we need to obviously implement the two. I'm just going to go ahead and make this a little easier for ourselves to read through the rules here. True. Okay, so we have two more here. We need to do indigo equals true, violet equals true, right? But we haven't actually finished all the rules, and that's why you're getting this error message right here, this number one. It's not even technically an error message. What it's saying is we did not implement all the different kinds of patterns for equality non-exhaustively, and you could certainly do this when you're doing deriving with the EQ, but you don't have to. But generally speaking, what you would normally want to do is you would want to take any other variation of any arguments, since you don't really care of any other variations, because these main variations are the actual truth ones. You could just simply use, there's a notation in Haskell that allows you to ignore the argument, or it's taking any arguments, and that's the underscore. You can simply just say, okay, for everything else, it's just not true, all right? And I just realized there's one more rule I forgot to add, which is green. Just one thing to remind people on this definition, and I know I'm probably beating a dead horse right now, but I'm just going to mention it anyway. Remember, for data constructors, you always want to capitalize the first letter of the data constructor, all right? It will actually complain if you don't, okay? I fell into that trap once. I'm not going to, I'm just giving it to you now so that you don't fall into the same trap before. So now that we have our primary colors defined, right? Our rainbow colors defined. Let me actually do this. Rainbow colors, okay? We could go ahead and define red. We could see that red and green are all constructed and so forth. We could see red equals red, or red equals blue is going to be false. We could also see that by defining the equality operator, we also get the not inequality operator. So the not equals is actually also available to us because it was generated for you. Again, to go back to what I was saying, since EQ is a very simple type, either you define equality or you define not equality. All right, and it's easier to technically define equality than not equality, just so that you get not equality for free, not equals for free. And you get all the different variables in there. You could, this will run the strict one that we just saw earlier, okay, versus the other one that we just saw, which is not equals yellow. That's actually what that behind the scenes is actually calling this guy and then just negating it. Okay. You can see though that that this is not a pre-baked, this is not a data type that was built into Haskell. Okay, we've defined a custom data type here, although it's not as spectacular in terms of what it is. It is something that's very simple. Okay, and you can get very fancy with this. Like, for example, if you have say our pair. Let's say that we took our pair that we just defined here. Okay. Actually, this would require a little bit more work because I have to actually also define first and last for these guys in order for me to implement EQ for pair. Let's see, what can I do to actually show one more thing? Okay, you know what? I'm going to take this one. This is an interesting one that that I wrote down from the date example that's available inside inside the Haskell book, which I think we should at least cover through and understand. This is in chapter 6, page 175 in the Haskell book if you're using the ebook version. And this is defining a date object, which we can define as date with day of the week, and our an integer indicating what is the date, the day of the week. And the way we define day of week is as we define like rainbow colors, which is Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Okay, and obviously this requires a little bit more if you're going to try and associate this with some sort of a calendar API. But the main thing to note is now that we've defined the day of the week and the date, we can implement instances on date by just simply writing a fairly complex rule here, and that is if we get two dates here, okay, date, week, day, and day of month, okay, and we get another rule, date, day prime, day of month, prime. This is equal to essentially whether or not day equals day prime and day of month equals day of month prime. You can see that what this is illustrating is that you don't necessarily need to have a fairly standard way of actually implementing equalities. You could write a proper predicate here. hold on a second, I can't see the error message here. Okay, so what is this? Warning noise rising from the use of EQ. Okay, got it. So we need to also implement this, which is instance EQ day of week where actually, you know what? Yeah, I'll just do this. This is not going to be that hard. So we do mon equals true. Tuesday equals true. Wednesday equals true. Thursday equals true. That was the issue that we saw earlier, what I was showing you in terms of the warning message. That happens because I did not define the EQ on this day of week. So now this should all be okay. So like I was saying, you don't necessarily need to have this kind of concrete rules necessarily for all your types. Okay, you could have a proper predicate defined for a given type, and as long as, you know, again, the primitive types that we're using are EQ themselves. Like, for example, you may have noticed I had to define something for day of week, but not for integer for date in order for this predicate to become a valid predicate. Well, that's because int is a numeric type, and numeric types are EQ. So EQ is already defined, equality is already defined for integers, so we don't necessarily need to go and re-implement that. Okay. Again, this here probably could have been automatically generated had I just used deriving, but I'm not using deriving right now for today's purposes, just because you need to get your feet wet in implementing this for the cases where you may need to actually say, okay, it looks like Haskell is not generating the right derivation, or Haskell can't seem to derive this automatically. I'm going to have to go and implement this myself and add my predicates myself. Okay. The bottom line is by doing that, you are essentially implementing what's it? You are essentially implementing rules on top of which, when they see instances of your type and those follow those rules, that particular operation gets executed. Okay, that's really what it is. Okay, that's what implementing a type class is doing, just like implementing an interface in other languages. But here, by doing so, your type class represents a more generic specification of operations that disjoint types may all necessarily implement. Okay, so it's a different type of type hierarchy than most people are technically accustomed to. So let me try something here, which is one, you may end up using something like this. Let's say 2 and 15th. Okay, no data constructors, not in scope. Oh, right, sorry. I'm using the wrong definition. There's 15th. So one thing to note about, and this is something that was slightly more different than what we were seeing before. And that is, at the time of the book's publishing, if you had ran this particular piece of code, okay, for folks who are actually using the Haskell book, you may have thought that you'd get an error message saying no instances of show and date occurs. What seems to be happening is there's now an implicit show that occurs here that's saying that this is of type date. I'm wondering if I add show here, what might happen. Let me do this. For some reason, that is not encountering. It's going to tell you the same thing. Okay. So it looks like there's an implicit show being defined already for you inside the newer versions of GHC. So folks who are looking at the Haskell book wondering why some errors are not showing up, it's because some other features have been added to the Haskell REPL since the time of the publication. So I'm going to, again, briefly take a break here and then check to see if there are any questions. Okay. So there's one more thing that I wanted to mention today in today's discussion, and that related to type classes. And this is sort of going to get started on another bit and piece of information. And that's related to partial function applications as well as partial function implementations. Okay. To illustrate this example, I'm going to get rid of one thing and show you an error message that might end up occurring to you during your Haskell journey. Let's say, for example, we saw already when we deleted, actually, if we don't provide an unconditional case that will generate the rest of the various different types of cases, that the Haskell editor, at least if you're using Dante with Emacs, okay, it will, and which hooks into the Haskell REPL. This does this for you. I think folks using Visual Studio Code or other implementations of languages, you may certainly encounter this in your development environment of choice as well. But you will end up getting some warning like this, which it says, okay, warning, incomplete patterns, pattern matchings are not exhaustive. Okay, and it will show you the different patterns that cannot be matched. And there might be multiple of these. But everything gets compiled and run. But when we actually go ahead and do our comparisons, we will see that while it works for anything that's already been defined, you're going to get something that is blown up into the REPL. All right, and it's something along the lines of non-exhaustive patterns and functions equals. The reason this is happening is because it basically did each of these rules becomes a lookup, right? And all the variations that that fall into the last parent, think of it like your default case in your case statement. It cannot be found, and because it can't be found, Haskell throws this exception saying, okay, this is non-exhaustive, you can do this. But this kind of sucks when you are writing REPL code and you're trying to do some stuff. So there's a feature in the Haskell REPL that you can do W-all. And this is kind of the same stuff that is essentially being used here. Okay. The only time that you would see this is if we try to do a strict load directly into your REPL. If you're using Dante or Emacs to automatically load your stuff into REPL, you're already getting some of this information available for you because I think the underlying configuration already gives you this. But I'm just showing you how this might look like in the REPL here for future sake, in case you're running this in, say, like the shell, and you're not entirely sure how to set this up. So you first set all warnings, and then you essentially load PC example, and you'll end up getting an error like this, which is the same error that we were seeing earlier, which is warning, pattern matches are non-exhaustive, and it shows you that there are patterns that do not actually occur in your pattern matching, and because pattern matchings are non-exhaustive, it's essentially saying if you don't finish the number of all the different patterns exhaustively, I'm going to throw an exception here. All right, so the only fix here that you could do is this, and you can now see that everything is properly loaded. We could see that if we do set, unfortunately, I don't think my setting is set up all the time. If we try loading TC example here, you can see that you get no warnings, everything is fine. And additionally, you notice in my editor window, I no longer have that warning message that we saw earlier. One of the nice things of using a development environment that gives you these warning messages, especially if WAll is turned on, is you can beat loading the file and seeing what happens in the REPL ahead of time. You will actually encounter these error messages and fix them very, very quickly. Okay. Partial function implementations and rules associated with those function implementations are not specific to implementing rules for type classes. You will see partial functions, and when I'm saying partial functions, I'm not talking about partial function applications. I'm talking about partially implemented functions. Functions whose cases are not completely defined in a clear way for all variable cases. All right. Haskell is, since it's leveraging pattern matching a lot to actually go verify particular rules to see if there's a cache results already available or it may need to compute something, you need to specify all the definitions for a specific rule in order for this to occur. All right. And nothing like actually makes this more illustrative than defining, say, a simple function, let's call it f, that takes a countably infinite set, like let's say integers, all right, and returning rules. And now you're going to have to write every rule for every function if you write it like this. Sometimes you might have f equals 1. F equals 2. Let's see if we load this, what might happen. You'll get a warning message saying, oh man, pattern matchings are non-exhaustive. Then you might end up adding more and more, and you'll keep on having to add it, and you will never actually complete all the rules. But you could also write, just a couple of these, and then write a rule that says, okay, everything else is just false. And by doing that, you've just automatically loaded that, and since you have this unconditional saying I only care about 1 and 2, but everything else is set to false, it's going to go ahead and say, okay, now all the different patterns are actually defined, and I can actually go ahead and do this, use this function without throwing an exception. Okay, you will never necessarily get an instance of something that does not have a rule associated with this. Okay, this pattern matching thing, the reason why I bring it up is this is kind of the basis, especially for how we might end up later on in other cases defining recursive functions. But if you're not familiar with what these patterns are actually doing, or you don't understand how these patterns actually work in the overall scheme of things, you will end up hitting this case where the the code is actually doing something that you didn't expect it to, and it'll throw an exception that you just saw here, saying that the pattern cannot be found, and non-exhaustively looked up for everything and couldn't find it. Another thing to note is when you're dealing with especially function countably infinite sets like int, is you only really need to necessarily deal with what's it? You'll end up necessarily dealing with a lot of cases, just because, for example, in the case of integer, you are talking about a signed integer that has a min bound and a max bound. If you recall what the min bound is, min bound int, min bound, max bound int. You can see that the number is huge, and it's just going to be the number of cases you might need to deal with are going to be numerous. All right. So one thing to kind of mitigate this, if you're defining functions to prevent this kind of pattern, is use a data type that isn't as big. If your data, especially if you know for a specific program or a specific use case, that you're only going to be dealing with a handful number of cases, make them into a sum type or a smaller type, so that way you don't have to use the primitive range in order for just don't use the primitive range, because you're going to end up having to deal with all these exhaustive cases. Okay. Another thing to mention is that I want to at least briefly mention regarding any of the primitive types, with the exception of maybe bool, is since they are going to be huge sets, don't try to do what you might do in languages such as C and use it as some sort of implicit sum type, just because that could end up causing the same partial function implementation problem that we were illustrating here. All right. Right. So we've already kind of touched base on this last thing, this last piece that I wanted to talk about today, with relation to EQ. But one thing that might be useful to be aware of, and that is what we were talking about, is sometimes you might end up wanting to write a type class implementation for something that's actually passing in itself to another type class, to a generic variable, and you want to be able to guarantee that that those type class constraints are adhered to prior to the instance being defined. Okay, we've seen this actually with some examples when we looked at the EQ type class itself. An example of what I'm talking about is something like this, okay, where you have essentially type class constraints on the input types that are being passed in before the type class instance itself gets executed here, okay. The notation of doing this to the arguments is to provide essentially those rules essentially has type constraints. How might we do this for, say, what we were just talking about for our own type class? Well, I think the easiest way to do this is to probably define an example here. This is an simple identity. I'm going to call this my ID. Okay. Um, this is similar. This is kind of the same thing like identity in the book, but I'm just going to shorten the name for simplicity's sake. And you might end up, defining, for example, an EQ on this my IDA. Notice for folks who are watching, type variables can be any type, and that includes instances of type classes. Okay, so my IDA is itself is a type that we are essentially explicitly constructing with the generic type variable A. Okay, and we might just define my ID V and my ID prime equals to whether or not these two are equal to each other. All right. So we just defined and we get this warning message saying that, well, wait a second, you just defined V associated with my ID, but we don't necessarily know from the inferencer whether or not V itself is EQ or not. And you don't necessarily want to go in and, do what I did, which is you could define EQ day of the week essentially as being integer and then having to specify, a specific instance for EQ for V, because we don't know what V is. V could be any type, okay? So the way to at least enforce this is by simply adding what I showed you earlier, which is a type rule, saying that, okay, by the way, anything that's being passed into this instance, make sure that the input type variable is an equality type variable before it can actually be passed into my identity. Okay. So now that this is defined, you can certainly use this in, say, my ID 5 equals my ID 5, and you'll end up getting, what? Did I mess that up? Hold on 1 second. Hold on 1 second. Okay, my ID 5. Defaulting EQ arises to use. Okay, so it looks like in order for me to actually leverage this, I'm going to have to create the instance itself. Okay, so let's say that I define x equals my ID 5. Okay, so what x is essentially a numeric that takes it. If we do x equals x, it should actually work, but for some reason it looks like it is not working as I expected to. Let's see if I could do... There's a type default, essentially, error that's coming here. EQ A0 arising from the use of... Okay. Let me see something here. Did I mess up? Oh, I may not have defined this. That's probably why it's causing that issue. Should have just checked to make sure that this is all defined. Okay, it says that it's there now. X does not exist because we reloaded. X equals my ID. Is it going to still throw an error? Yeah, it's going to throw an error because I don't have probably a no EQ associated with it. Okay, so the reason why this isn't working is because we don't know anything about the actual underlying type, which we do in this particular case. We added the same type constraints for this information, so this actually would technically compile, but because we don't necessarily have the values at compile time, it's throwing up this particular this issue. It's dealing with essentially two different equality operators that are both perfectly valid. One is the identity one, and the other one is the numeric one. All right, that's kind of what the issue is. There's essentially in this example two versions that could be used for the comparison operator. So give me a second here. I think one way of fixing this is, let's see if I do x equals ID of Monday. Oh, sorry, y, because it's a different thing. Okay, so y equals y. Okay, so this works because of the fact that this is defined as a simple rule, okay, that we just return true, and it doesn't actually conflict with the actual numeric type constraint that was added to x, as you see here. What? Wait a second. It says warning. Oh. Y is also my ID. So if we do max my ID 5, x is now my ID 5. So if we do x equals x, we'll get this error message, right? And it's because of the fact that we have a numeric type class associated with it. So it's going to attempt to essentially apply two things. Whereas with y, it's clear what to apply to. It's clear that we need to apply the myID equality type class to actually go and look up. This is the kind of stuff that you may end up encountering when you're developing, where you have these conflicting lookups, essentially. So this example here is saying, I don't know which equality operator you're asking me to call, because I found two associated with this rule. All right, one based on the inferencer, and the other based on the rule that we've defined with myID. So be careful in terms of some of those rules that might end up screwing up and ending up doing long debugging that we've talked about. All right, that's all I had for today. I didn't realize, like I said, this particular section is going to take a little bit of time. We're going to go through a couple of more examples next week on type classes, specifically numeric. We're going to go through ordering. What are this error message that we saw called type defaulting type classes. We're going to go into more details about that next week, what that means, and how to potentially fix it. Additionally, we're going to go through some of the other ones that we just saw with respect to what's defined for bool. And those are, ordinals, the ordering type class, the enumerated type class, show and read, and essentially we're going to be taking a look at from this to culminate into how do we do type dispatch based on the type class instances and how that works with concrete types. Are there any final questions? Any comments? All right. I appreciate you guys joining me this Sunday. I hope you guys, the folks who are international, I hope you guys have a great evening. Those who are in the States, have a good day, and enjoy the sunshine in your respective parts of the nation.